Now, what we will be doing in this lecture is, okay, we'll be designing the signal conditioning circuit as a whole. Okay, whatever the circuits that we have discussed up till, we will try to use then these circuits to solve some problems. Overall design of the signal conditioning circuit. Uh, this is the parameter to be measured of the process. Can be temperature, pressure, flow, velocity, and whatnot, speed, etc. This is this the process parameter has certain range from Cmin to Cmax. The sensor output has certain range. Sensor can be temperature sensor, pressure sensor, flow sensor, or whatever it is, depending upon this parameter. And then it has a range of Y min to max. Then we have to design the signal conditioning circuit for this parameter in particular range of V min to Vmax. Okay. So there are three types of parameters then. One, process parameter actually to be measured. When the sensor senses and converts into voltage or current, whatever it is, its range, right, or temperature, whatever. Input so that the input impedance will be very high. Okay. The output impedance, it should be very low to avoid the loading. Okay. So these are the actually three parts of the signal conditioning circuits that have to be considered while design. Okay. Oral guidelines. First, general guidelines. If the input is resistance change, like RTD or thermistor, or and a bridge or divider must be used, be sure to consider both effects of output nonlinearity with the resistance and the effect of current with the sensor, resistive sensor. Okay. If it is nonlinear, then it has to be linearized. Okay. And maximum current capability of that sensor resistor, if it is a resistor or a bridge, okay, or a voltage divider, the maximum current capability, current carrying capacity of the resistor must be considered. Okay, otherwise the sensor will be damaged. For operational amplifier portion of the design, the easiest design approach is to develop an equation of the output versus input. Okay, so when we are designing the circuit using op-amp, we will find the transfer function. It is transfer function equation, that is what is the relation between output and input. From this equation, it will be clear that what type of circuit must be used. Okay, so depending upon the equation of bit of input and output, we will select the components op amps of the circuit. Okay, which circuit op amp circuit is to be used. So this equation represents static transfer function of the signal conditioning. Okay, always consider any possible loading of the voltage sources by signal conditioning. Such loading gives a direct error in the measurement system, and that should be avoided. So if it is low input impedance at the input, then circuits of high input impedance must be adequate, like voltage follower. Or if it is low output impedance at the output of the device, then a low resistance must be connected in parallel so that the output impedance will be low. Okay, so this should be taken into consideration. This is general. Okay, these are the general guidelines then. So let's solve one example on that. So this example says that we are required to develop an signal conditioning circuit for this, right? Excuse me, just for the disturbance. Sorry. Okay, and the sensor output is given. Range of the sensor output is minus 2.4 to minus 1.1 volt. Okay, so it is thermistor. So it is giving the output voltage of minus 2, ranging from minus 2.4 volt to minus 1.1 volt. Okay, and but we are want design for interface of an AD converter. This needs to be output to be 0.0 to 2.5. Okay, so input from the sensor is minus 2.4 to minus 1.1. Output of the signal conditioning circuit that is wanted is 0 to 0.25. Going to the circuits that we this figure here. So this is given minus 2.4, rather minus 2.4 and minus 1.1, whereas this is 0 and 2.5. So this part is not specified actually. So we are given. Similarly, this part is also not specified. Only signal conditioning circuit part is to be designed. So this range is given and this range is given. In this particular problem, the process parameters is not specified and the sensor is also not specified. Only output of the sensor is specified. So this is that way a simple problem or half the problem, and therefore we will be designing signal conditioning circuit only. So for that we need to find out the relation between this and this, V in and V out. Okay. So once relation is known, then we can uh, decide what type of circuit is to be used, whether it is inverting amplifier, whether it is non-inverting amplifier, a summing amplifier, an integrator, a differentiator, or voltage to current converter. Which circuit to be used will depend upon the relation between output and input. Okay, so let's find the expression. The first thing is to find out the expression between output voltage and input voltage, right? And the ranges of both are given in the numerical problem. What are the range? Output ranges from 0 to 2.5 and input ranges from minus 2.4 to minus 1.5, right? So let's solve it. I'll take it to some different file where the solution is there. solution. The solution was stored. Okay, we start this solution then. Okay, this here is the solution then. Same problem is written here. The sensor output voltage minus 2.4 to 1.1. For interface of an AD converter, this needs to be 0 to 2.5. Develop the required signal conditioning circuit. Okay. So, as I said, no information about the type of sensor is given, and therefore, first step of designing the sensor is not necessary. We are asked to provide voltage to voltage conversion from sensor output to the signal conditioning output. Okay. Since the sensor source impedance is not known, sensor impedance is not known. Okay, assume it to be high, because if it were low, then that would have been mentioned there. Okay, and would have to take the measures to make it high. But since no information is given, let's assume it is high input impedance at the sensor level. Okay, so input impedance to signal conditioning circuit that we are designing is assumed to be high. Okay, so input impedance of the AD converter, the signal conditioning output is to be given. It is specified that it is to be given to the AD converter, right? So AD converter, it has already high input impedance of the order of many of the kilo ohms, okay, near to mega ohms, and further the output impedance we will be designing the circuit with op amps, and op amp has low input impedance, right? So that's the no question then in considering the input impedance, right? Uh, since both input and output voltages ranges are specified, let's express output in terms of input voltage. So this expression actually we want to find out. So let us assume that expression as input output relationship as V out. Since it is to be linear, we are assuming the equation of a straight line y is equal to mx plus c, right? So V out has to be linear with V in, and therefore y is equal to m into V in plus VO, where VO is a fixed bias voltage, right? So it is a straight line equation. V out is equal to y is equal to mx plus c type. So V out range is given as minus 2.4 to minus 1.1. V in range is given as 0 to 2.5. I think it's reverse, wrongly written. Please correct it. Please correct it. V in is minus 2.4 to minus 1.1, and V out is 0 to 2.5. Okay, so it means that minus 2.5 corresponds in V in corresponds to 0 out, and minus 1.1 V in corresponds to 2.5 of out. Right. So moving further, so substituting these values of V in and V out, okay, we get two equations then. For this 0, our equation is what we have assumed: V out is equal to m V in plus VO. So V in and V out are known. So 0 is equal to m is as it is and minus 2.4. So 0 corresponds to minus 2.4 plus VO. So from this, what we get is VO is equal to 2.4 m. Okay, and for the second equation, it's 2.5 is equal to minus 1.1 m plus VO, right? So substituting, we get m is equal to 1.923 and VO is equal to 4.615. Okay, these are just the mathematical calculations. So m we have got it to be 1.923 and VO we have got it to be 4.615. So hence required range of output from 0 to 2.5 to be achieved for input range of minus 2.4 to 1.1. Using the expression, that is transfer function equation, V out should be equal to M is 1.923 into V in plus 4. V out is, or rather VO. VO, rather I'll call it as V naught or V0, right? Fixed bias. This is not output voltage. Output voltage is here. So 1.923 into V in plus V naught, what I'll call it as hereafter, 4.615. Okay, so this equation is now found out. We have to implement this equation using our op-amp circuits, basic op-amp circuit that we have studied up till. Okay, so what is your suggestion? What can we use? Did you understand the question? My question is, if this is the output expression, which circuit can be used? Any suggestion? Any suggestion? Of course, it should be op-amp circuit. So there is sum, meaning a summing amplifier will be required. Okay. Sum of two terms. So a fixed term and a variable term. Okay. Variable term has a gain. Being into this gain. So we will use a summing amplifier. Okay. That is what is seen from the expression. So V out should be the circuit, op-amp circuit to be used should be summing amplifier. It can be implemented in various ways. This is one of the possible ways that we are using summing amplifier. It can be done in many ways. Okay. So first part is the summing amplifier. Okay. How should be the summing amplifier then? It is non-inverting summing amplifier. So this terminal is grounded, and this terminal is given fixed bias VO, which is 4.615, and this is R2 and R1, right? So this will be output will be weighted sum, R2 by R1 into V in plus VO. So R2 by R1 should be 1.923. Are you getting me? Here, what will the output expression? R2 divided by Rn into V in plus VO, fixed voltage, right? So for this much gain should be adjusted. For adjusting this gain, the resistor selected that we will see later, but resistance of 19.23 is selected here, K is selected here at 10K. So 19.23 divided by 10K will be 1.923, and here VO is directly going, right? So this is summing amplifier, but the main problem is this summing amplifier is the input impedance is not so high. So if this is used, then here is the sensor. This input is coming from sensor. So the sensor will be loaded. Loading effect will occur. Right? This will draw circuit. This circuit will draw from the sensor itself, and output will not be correct. Okay. So here, at the input, to increase the input impedance, voltage follower is used. Voltage follower circuit you might be knowing. Okay. This is voltage follower. This is the voltage follower circuit. So non-inverting terminal is connected to V in, and inverting terminal is directly given here. So this gain is unity. So it's voltage follower. Whatever is V in, same will be here, but its input impedance will be very high because it's an op-amp. So loading effects of earlier stage, that is sensor stage, will be avoided. Okay, and this is VO. Still, it is a summing amplifier. This is a summing amplifier with V in coming from this voltage follower, and this bias voltage VO, which is 4.615. So 19.23K divided by 10K into V in, okay, plus VO. Now, another thing is that here the op amp is in inverting mode, right? This is an inverting of summing amplifier. So output will be negative. So what is the solution then? Output has to be inverted, right? So unity gain uh, inverting amplifier must be used then. Okay. After this, so what is it? Since the summing amplifier is in inverting mode, output will be negative. Hence, to get positive voltage, an inverter is required. So the total circuit is shown here now. It's you have to bear with this circuit. Okay. So this is the voltage follower. What is the purpose of voltage follower? To increase the input impedance. Right. So this is okay. The inverting amplifier with gain 1.923, 19.23 divided by 10. Right. So here we get it to be 1.923 into V in. So the term here is 1.923 into V in. Okay. The first term 1.923 into V in. Whereas uh, this is 10K and this is 10K. So R3 divided by R4. Right. R3 divided by R4 is 1. So this is gain is unity. But since it is inverting amplifier, this is inverting, so it will be negative. This negative will be again inverted and we get positive here. So gain will be unity. Further, the bias voltage VO, V0, rather, bias voltage V0 is added here at this point. So this is a summing amplifier. 1.923 into V in coming from this side and bias voltage V0 coming from this side at this point. So these two are added together and we get what is 1.923 into V plus VO, right? So this is the summing amplifier. By the way, uh, here is the 15 volt supply.
Sir,
And
we
here what
cannot
we
see
require
this
at
picture
this
of the
point is V0 that we have calculated 2.4, right? V0 already we have earlier we have calculated, na? V0 is rather 4.6, right? Into M is 1.923, right? So for this circuit, here is the M coming from this, and here is 2.4 at this step. Okay, so
Hello, sir.
this voltage will be added to this
Hello.
2.4, and the output voltage equation will be 1.923 into V in plus VU, right? 1.923 into 2.4, right? So M into 2.4 will be the
Hello.
total output. Okay, so required bias voltage of 2.4 is provided by the voltage divider of 10K by 1K. This is pot. Okay, 10K and pot 1K. So the voltage can be adjusted by this pot. Okay, so a voltage divider circuit is used. So this resistor is additional one. Okay, this is the register for
Sir.
it is in the output impedance. Okay?
Hello.
So if it is given to the AD converter, the output impedance of amplifier is, if it is low to the high, then it can be lowered by connecting this resistance
Hello.
like this to the ground. Okay, so this is how they design. Now the values, how they are selected, all the
Sir.
values, how
Hello,
they
sir.
are selected. Okay,
Sir.
this was the circuit actually
Sir,
according to the expression. Now the selection of the values. Okay. So this expression is got V out is equal to 1.923 into V in plus 2.4. Right. So this expression we have got it.
Hello.
So the gain of
Hello.
1.923 is required. So R2 divided by R1 should be equal to this. So R2 is selected as 19.23 and R1 is selected as 10K. So that the division ratio will be 1.923 for op amp number 2. Right. For the bias voltage of VO, voltage divider of 10K fixed and 1K part is selected so that the voltage across 10K resistor can be adjusted to equal to 2.4 and that then multiplied by 1.23 will give the bias voltage 4.65. Okay, so R3 and R4 are selected equal to 10K, keeping in mind that the maximum current carrying capability of the op amp, which is, as we have discussed many times, 20 to 25 milliamperes. So we cannot select this in ohms or mega ohms, right? So they are 10K are used, keeping in mind the current carrying, maximum current carrying capability of the op amp 3, right? That is summing amplifier. And the 100 ohm resistor is used for keeping loading effect of op amp small. So this is how. What was the question? Once again, we visit the question. Okay. The question was, sensor output was given like this, and required output of the signal conditioning circuit was from this to range. Okay, and we were asked to uh, design a signal conditioning circuit which will change the sensor output to signal conditioning circuit output to like this. Okay, so that is the range. So we took this range minus 2.4 to 0 and we minus 1.1 to 2.5, and we found the expression and we implemented that expression. Okay, if it is op amp circuit, then generally we uh, find the expression and then decide which op amp circuit will be best suited for these expression, implementing this expression. Okay, uh, I think I have explained from my side. Let me know in the chat box, did you understand or not? Let
Hello,
me go to the
sir.
meet and let me go
Hello,
see the chat. Okay.
sir.
Wow.
Can you hear us? Can you hear us? Hello.
Circuit diagram, yes. Yes, yes. Uh, let me check your post.
अरे यार.
कॉल कर रहे हैं व्हाट्सएप पे कॉल कर सर को
Image was that way.
Hello, sir. Can you hear us?
Okay,
Hello.
Okay, I'll
व्हाट्सएप कॉल कर अरे
take
ब्रदर
the final circuit image once
Devashri,
again
can you hear me?
and put it
हाँ भाई सुनाई दे
in
रहा
a
है
separate part.
अरे सर को कॉल करो.
येतोय येतोय ऐकायला येतोय मला तुझा
कॉल कर
Sir, you can't hear us.
Just a minute.
Please do
Photograph of this.
something.
Please excuse me, please, just for a minute. I'll take photograph of the circuit and I'll show you
Yes.
again. Right? Just for a moment. Wait it. No. No one talk to me. I could not hear any one of you. नाही मला आवाज नाही आला कोणाचा.
सर आता येतोय. आता पण नाही. वा.
Sorry, I did not see the chat. Earlier. At least my voice is reaching you.
Sick. This is a joke.
Shall I explain it once again? Can you hear me? Am I audible? Please type.
यस सर
Yes. Okay. I'll just take a photograph of this circuit once again and I'll show you. Just a minute. Just hold for a few seconds. Please. थोड़ा क्लियर कट दिसेल. Unfortunately. Just a moment, I'll show you the circuit. Okay. Actually, it was scanned using Adobe Circuit, na? So that's why I could. It is a scanned image. I'll show it again. Happened. It's not downloading. It's taking too much time. Just a minute, hold please. Is the image visible now? Let me edit and just crop it. So that. Okay, anyway, let it be. Is the image visible now? Like crop it or not? Should be visible now. Can you see?
Yes, sir.
Yes, sir.
God kill me.
Sorry for inconvenience. Okay. Is it visible? Image was. Could you see that image? I'll go to again. Yes. Okay. Yes. Okay. I'll go to it. So this was actually the image. Okay. Uh, right. So this is the summing amplifier. Right. This is the summing amplifier. Inverting summing amplifier. And this is the inverting amplifier, which is providing the gain of 1.923. Right. This is 1.923. And Vin is coming here. This is the voltage follower circuit used for high input impedance, right? So summing amplifier has low input impedance, therefore we add the voltage follower here, which has very high input impedance, and it will directly follow whatever the input voltage is the output voltage here, right? So Vin into gain R2 by R1. here the voltage is 1.923 into Vin, and then this bias is added. Here is the 15 volt supply voltage. This is 10K and 1K. It's a voltage divider circuit, right? And this voltage across 10K is provided, or rather added, to this output of this inverting amplifier. Output of this inverting amplifier is 1.923 into V in, and plus this voltage of V naught is added to it, and with a gain of 1, R3 upon R4, this gain of 1 is the output voltage. So output expression of V out is equal to V in into 1.923 and 1.93 into 2.4 volt adjusted here. See it. This voltage is 2.4 volt adjusted using this part, right? And this resistance just is for lowering the output impedance of the op amp. Okay, so this is how we design the signal conditioning circuit for given problem. Is it okay now? Please let me know. Is it okay now? Yes, I'll be sharing everything with you, all the PPTs. As like earlier one, I'll be sharing all PPTs with you, right? That's no problem. Right. Okay. We have still 15 minutes and we'll go to the next problem then. Try to complete it, but if remains uncompleted, you complete it at home then. Okay. So let's go to the problem number 2 then. Okay. And where it is? Yes, it's here. Second problem. Is it visible now? Is this file visible?
Yes.
What's the problem? I can't hear you, anyone. What must be the problem? Yes, now please someone unmute and just talk something.
Hello.
Unmute and talk something.
Mic testing 1 2 3.
I have removed my earphones now.
Hello.
Still, I am not receiving any voice.
You still can't hear us, sir. I'm saying as I
Okay, I removed the earphones now.
typing this.
I'm using the
I'm
audio output of the
hello.
laptop now.
Hello. Hello.
Hello.
Anyway,
आणि आपला आवाज नाही जात.
there's some technical problem.
सरांना नाही येत आपला आवाज. You can't hear us. IDKY.
Let me change my earphone and let's see. I can hear or not. Yes, I. Now I have changed the earphones and
Hello.
someone
Hello.
unmute and talk then.
Hello. 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 Hello.
Hello.
Hi, कोणी कसा आहेस?
Hello. No, I can't hear. It's not from my end actually.
सरांना अनम्यूट करून व्हिडिओ करून दाखवू का? सर am I visible?
Hello. Yeah.
तुझा पाय दिसतोय फक्त.
हा ते असू दे पाय
There is no voice.
खरंच सरांना आवाज नाही.
hello.
No, I can't actually hear.
ब्रो तू डेंजरस दिसतोय.
सोड रे जाऊ दे.
Okay, let the problem be there. We will communicate from this. It might be from my side also, but let's not waste the time in that. So we'll communicate through chat. Okay, let's go to problem number 2 then. Okay, So my question was, is this file visible or not? Okay, tell me in the chat, is this file visible or not? Just I should. Okay, that's visible. So let's continue then. Right? Let's continue with the second problem. Let me read the problem first. Okay, read with me. The temperature is to be measured in the range of 250 to 450 degrees Celsius. Okay, with an accuracy of plus or minus 2 degrees Celsius. Okay, so from our side, here, this is the temperature and its minimum and maximum limit with accuracy are given. C min, C max of the process parameter. Process parameter is temperature, right? Parameter is temperature, and its range is given as 250 to 450, accuracy plus or minus 2, right? It should be linear, and noise specifications are not given, right? So coming to this one, the sensor is a resistance that varies linearly from 280 ohms to 1060 ohms for a given temperature range. Okay, so 250 to 450, it corresponds to 280 to 1060, right? So sensor output range is also given. It means that we are here, Y min and Y max is given. So this C min, C max is given, Y min, Y max is given, right? So next is develops an analog signal conditioning circuit that provides the voltage varying linearly from -5 to +5. Okay, -5 to +5, meaning this output range is given, signal conditioning. So all input, all minimum maximum ranges are given, right? The load is high impedance recorder, high impedance recorder. So input impedance of the output device, whatever the recorder, that's no problem then. What condition is given? The power dissipated by the sensor must be less than 5 milliwatt. Okay, so according to guidelines, what we say for the sensor, power requirement range is given. So with this, we will then start the design. Let us go as per guidelines then that we have seen. Measured variable parameter, temperature ranging from 250 to 450. Okay, accuracy plus or minus 2 degrees Celsius. Okay, at low end, percentage accuracy will be 2 divided by 250, 0.8%. At higher end, 2 divided by 450, it is 0.44%. Okay, noise is not specified. For sensor signal, parameter is resistance, transfer function is linear, time response is not given, range is 280 to 106, that is linear one, and power is maximum 5 milliwatt sensor. Okay. For signal conditioning circuit, parameter is voltage, that is linear, range is given as -5 to +5, input impedance to keep the power in the sensor below 5 milliwatt. For signal conditioning circuit, output impedance is no problem because high impedance recorder is connected to the output of the signal conditioning circuit. So as per guidelines, these are the specifications given. Okay, so accuracy ranges from 0.8% to 0.44%, right? So let us be on safer side. So let us select 0.1% to keep three significant digit, meaning after decimal, the it will be available at 0.000 or to 0.999, 3 decimal point, 3 significant figures meaning 3 decimal points. Okay. Now, to keep the sensor power dissipation below 5 milliwatts, the current must be limited, right? So, how much should be the current then? Power is given, okay, and sensor resistance range we know. Okay, so maximum current will be corresponding to this maximum power dissipation. I is equal to power 5 milliwatt 0.005 watt divided by resistance 1060. Okay, current will be minimum if R is maximum. So current should be kept minimum. Okay, we should not design with maximum current. When will be the maximum current? Maximum current will be when the resistance is minimum. We should not design with that current. We should design with minimum current, right? And the minimum current will be when the resistance is maximum. Okay, so this is misleading. I have taken 1060. This should be confusing actually. Why I have taken for current as 1060? Because I should design with minimum current. Okay, minimum current. So if I take the current range to be corresponding to 280, the current will be high and that may exceed the power dissipation capacity. So the current what I am calculating should be minimum as possible. 0.005 divided by the resistance 1060. That's maximum resistance. And this comes out to be 2.17 milliamperes. Okay. So this is the limiting current corresponding to maximum power dissipation of 5 milliwatts. Okay. There is no issue now. Shall I check the chat box then? Yes, there is no issue now. Okay, let's continue. Okay. So let's select less than this on to be on safer side. Instead of 2.17, let us select the current to be 2 milliamperes so that the power will never go above 5 milliwatt. Okay. So one thing is clear then, current is calculated so that so we must take care while selecting the resistances to be connected to the op amp. Okay, they should not carry more than 2 milliamperes. Okay, so while considering the circuit to be designed, the resistors, the sensor, where is the sensor connected, that sensor should not carry current more than 2 milliamperes. Okay, now the system must be linear. Okay, so we have to find out the relation between sensor resistance and the output voltage. Okay, since the system is to be linear, then let's select once again the straight line equation y is equal to mx plus c. Okay, here the input is resistance whereas output is voltage. So we want to find out the relation between sensor resistance, which has a range of 280 to 1060, and signal the output, which is 5 minus 5 to 5, right? So with this expression, substituting the values of RS and V out, okay, as in last problem, just substitute the values. 280 corresponds to minus 5, 1060 corresponds to plus 5, okay, and solving this as in last case, we get m is equal to this and v naught is equal to this. Okay, so final expression, the transfer function equation, we get it to be 0.0128 into RS minus this is negative minus 8.5. Okay, and again the question of implementing this. Okay, so how it is implemented then? So I have shown the final circuit. You do the design at home. That will be homework. Okay, I have designed it, but you design it at home. Okay, see the final circuit. How it is? Here is a voltage divider circuit. Here is a voltage divider circuit. Okay. What is the output voltage? What should be the output voltage? 0.012 into RS minus 8.58. Okay. So rest I am leaving it to you. Okay. How it is, how the values are selected. By the way, I'll tell one thing. that the sensor is connected in feedback circuit. Sensor resistance, whatever it is connected here in the feedback circuit. Okay, this is for bias V0. Okay, as in last problem, it's similar one. Okay, 10K, and the gain is adjusted. See here to give 8.58. Here. Okay, whatever the voltage here, that should be multiplied by the gain, and that should be minus 8.58. Okay, and from this, what should come at this? It should be 0.12 into RS. So this we should get here at this point. Okay, and the circuit is designed according to that. Then. Okay, so whatever the sensor resistance, we should get it 0.001 here, and then multiplied by this gain, right? 10K divided by 781, we will get this gain R3 divided by R4 into this. We will get it to be 0.012 into RS, right? So do the rest of the work at home then. Okay, I have shown some points here. Okay, explain some points here, but do it at home then. So once you find the expression between input and output, this is the input and this is the output, then it will be easier to design the circuit. Okay, it is the question now of selecting the components and selecting the values of the components. Okay. Let me have feedback. Are you understanding this or not? Just say yes or no. That's okay. Yes. So our about circuits are over now. We will go to the transmitters then in next lectures. Okay, transmitters. Especially important thing in this is 2-wire and 3-wire transmitters and P2I converter and I2P converter. That are the important points here. And then chapter 2 will be over. Okay, probably on Monday. I'll try to complete this chapter because it is taking too long actually. Okay, might be I'll be calling for some extra lectures to cope up with the time. Okay, but at present, let's complete this chapter. Okay, so op-amp based circuits are over now, and it must have given you the idea how to design the signal conditioning circuit using op-amps with various circuits. Okay, thank you then, and let me mark the attendance. I have not. Okay, mark the attendance. Then leaving the meeting then. Thank you.